Hi, this is Gustav Nelson with video 3B for Calculus 1, and here we have a problem where we want a cylinder with a volume of 105 cubic feet and whose material for the wall will cost $3 per square foot. The bottom of the tank will cost $7 per square foot, and the top of the tank will cost $2 per square foot. And we were asked to find the dimensions that will minimize the cost as well as what the minimum cost is. So the way we're going to have to do this is find an equation that tells us the cost of the tank in only one variable, so either the radius or the height. And then we're going to find the derivative of that equation, and then we're going to find the critical point where the x value causes the derivative to equal 0, which should be either the highest cost or the lowest cost. In this case, we're looking for the lowest cost, which would be the relative minimum. And then we'll plug that radius back into height, so we'll have both the height and the radius, and then we can plug that into the original cost equation to get the cost. All right, so first thing we got to do is relate the height to the radius, and we do that through the volume. So we know that we have a volume of 105 feet cubed. We know the volume of a cylinder is pi r squared, which is the area of the circle, times h, which is the height. So all this equals 105. We can rewrite that as h equals 105 over pi r squared, and we'll plug that back in later. Now we need the equation for the actual cost. So for the cost of the wall, that is going to be the circumference of that circle times the height, so 2 pi r times h, and that's $3 per square foot, plus the bottom, which is $7 per square foot, which is $7 times the area, which is pi r squared, plus the top, which is $2 per pi r squared. So we can rewrite this having 6 pi r h plus 9 pi r squared. And then we can plug in this h to right here. So now we have 6 pi r times 105 over pi r squared. That pi and one of those r's cancels out, leaving an r at the bottom. So now we have 630 over r plus 9 pi r squared. We're going to find the derivative of that cost. So here, take the derivative dc over dr. Here, dc over dr. So now we have the derivative of the cost and the derivative equation all in terms of the radius. So negative 30 over r squared plus 18 pi r. Remember that over r can be the same thing as 630 times r to the negative first. So when we're actually finding the derivative of that, the derivative of this portion, you just do the same thing, have that basically negative 1 times this number, and then minus 1, so now it's technically negative 30 times r to the negative second. We're going to set that to 0. The first critical point we're going to find is we can factor out an r. So now it's, instead of negative 630 over r squared plus 18 pi r, we have r times negative 630 over r cubed plus 18 pi. Factoring out that r, we know one of the critical points is actually going to be 0. Of course, we can't use that because in real life we can't have a negative radius. And so now we just rewrite this equation: minus 18 pi over here, r cubed comes over here, and then negative 30 divided by 18, negative 18 pi right here. These two negatives cancel out. You take the cube root of r to the r cubed and the cube root of this, so you get r equals 2.2334. And so that, if we did everything right, that should be the second critical point of our derivative cost equation. And the way we can check this is type the derivative equation into your calculator. When you find the r value stored into one of your letter things, go here. So you see I've already typed it in there. I'm going to do it again. And you should get, in this case, we don't actually get a 0 because I don't think it can calculate that deep in. But you see we have directly after it, it's 16.248. Directly before it is negative 17.77. And at where our critical point is, it's 9.4 times 10 to the negative 8th, which is essentially 0. So I think we can clearly see that this is the critical point. It's basically 0 right here. It's negative before, and it's positive after. When we write the critical point chart, we see that this is our 0 point. Before it is negative, after it's positive, and so that would draw a relative minimum point. So we can know that this actually is the lowest point in terms of cost. All right, so after we have that, we can solve for h. So h equals 105 over pi r squared. 105 divided by pi times 2.2334 squared equals about 6.7. So we know the radius is 2.2334 feet. H is 6.7 feet. We can plug we actually just use the r value and plug that into the cost, and we get about $423.12. And that's it.